Hello students, today is our class on fluid mechanics part 2. We have already covered some parts of fluid mechanics like Pascal laws, etc. So in today's class Hello students, we'll be covering fluid mechanics part 2. In the last class we have covered the first part of fluid mechanics, in which we covered Pascal's law and other parts of fluid mechanics which were quite basics. Now in this part we will cover later parts like viscosity, Stokes law, terminal velocity, streamline and turbulent flow, the concept of Reynolds number, and Bernoulli's principles. So we have these points to cover. First we'll look into what is viscosity. Then we'll go through what is Stokes law and how it determines terminal velocity. Then we'll differentiate between streamline and terminal flow. And we'll also come to know that how Reynolds number is an important factor in determining whether a flow would be streamline or terminal. Then we will apply Bernoulli's principle and we will try to solve some questions based on this. So let's start with viscosity. So what is viscosity? Viscosity is kind of friction between layers of a liquid or any kind of fluid. Fluid is anything that flows, like air also is a fluid. Any kind of gas or any kind of liquid is a fluid. Sometimes some solids also flow. You might have heard that pitch or say coal tar. You might have seen this is a very common substance. It is used to build roads. हिंदी में इसे अलकतरा भी बोलते हैं. So coal tar is a solid that under some conditions of pressure and temperature it flows. So viscosity is related term with any kind of material that can flow. So suppose there is a flow and there are two layers which are flowing over each other. Let us magnify this part. So you see that two layers, layer A and layer B. You can say that layer B is above it and there is a relative motion between these two layers. So say layer B is moving with respect to layer A with velocity v, and some force is being acted by A on B and at the same time B on A by B. That is the mutual force acting between the two. You can simply relate it with the Newton's third law that two objects, whenever object 1 is exerting a force on object 2 is also exerting the same amount of force but in opposite direction. So same this force here, this is a kind of frictional force but in liquids, and this force is called force of viscosity. Let us try to analyze this situation in a very ideal form. Let's say this is a container containing some kind of liquid, and the depth is h. You can also say the height is h, and some plate is put over it. You can assume that this plate is floating over the liquid surface. So what I'm doing, I'm applying a force F on this floating surface, or say this floating solid surface which is floating on the surface of this liquid, and because of this there's a velocity v on this plank or this substance. So you can say that this force F is creating a constant velocity, and whenever there is a constant velocity, that means there is no acceleration. That means the net force on this part, on this solid surface or solid object, floating object, is 0. That means there's another force F is acting on it, opposite to the applied force. So this force F acting in opposite direction is the force of viscosity. Let us write it as F viscosity, viscosity being in the subscript. Now this force F viscosity, or the force of viscosity, depends on what criterias, what क्या फैक्टर्स हैं जिन पे इस फोर्स ऑफ विस्कोसिटी डिपेंड करता है. फर्स्ट, टाइप ऑफ लिक्विड. सो इट मे बी वाटर, इट मे बी हनी, इट मे बी ग्लिसरीन, or some kind of lubricant. So all these kinds of liquid have different kinds of viscosity associated with them. What do we know about that characteristic? That characteristic is given a symbol eta. We write like this. Eta is called the coefficient of viscosity. So here we came to know that force depends on eta. That is one of the characteristics of any liquid in which that force is being accounted for. So let us consider another characteristics. So force of viscosity depend on first eta, which is coefficient of viscosity. Then it depends on area. Area A being surface area of contact. So you might remember that a frictional force doesn't depend on area of contact. Like if I'm placing one object on another, suppose this is the surface and this is the orientation of this object. So I may place on this surface, or I may place this surface down like this, and I calculate by exerting a force. I will find out the friction. Force of friction will always be the same. It will only depend on total mass and the type of surface, but this will not be applied in the force of viscosity. In force of viscosity, other than the coefficient of viscosity, we have area, surface area of contact. And another factor is the velocity gradient. So what is velocity gradient? Let us try and explain this on another sheet. Suppose this is a container filled with a liquid. Another object is there and it is being pulled by a force F and velocity V. So the layer along with this will also be moving with the velocity V. Same, this layer will pull with itself the layer below it, and something like that will go on to a depth. So let's say this is V1, V2, V3, and at some depth this becomes Vn equals 0. Means obviously at some depth the velocity or the speed of layer of liquids will go to 0, because its effect, the drag effect, will go on decreasing over depth. So you can say that with the depth or with the vertical downward direction, as y increases, downwards, the velocity decreases. And this is what the relationship of v versus y. So dv by dy, or say the velocity gradient, this is known as velocity gradient. So this is what we were talking about, velocity gradient. Now let us try to summarize this whole information into an equation. First, force of viscosity is proportional to area, right? Force of viscosity is again proportional to what? The coefficient of viscosity of that liquid. And force of viscosity, or say this is a different term, we will not say this is proportional to, we will use this at the last in the equation. Force of viscosity is also proportional to this velocity gradient. Both these two, let's incorporate this into another equation. force of viscosity is proportional to A, area of contact, times dv by dy, which is area of contact into velocity gradient. Now, to remove this what we call the sign of coefficient, sign of proportionality, we need to use a coefficient of proportionality like we do in force, like force is proportional to acceleration, and the coefficient, or say the proportional thing, would be mass. So force equals to mass times acceleration. Similarly, force of viscosity here is equal to eta times, eta being the coefficient of viscosity, which depends on the properties of the liquid which is being discussed here. So it may be water, honey, or glycerin, as we discussed earlier, times dv by dy. So this is our equation, force of viscosity. Okay, eta being coefficient of viscosity, A, area of contact, and dv by dy is velocity gradient. That is the function, or say the differentiation of velocity with respect to the depth. So after viscosity, we'll discuss Stokes Law. So you might have been in a storm, or you might have experienced swimming in a current. Current, I would say current of a river, current of water, not an electric current. So Stokes Law says that whenever a solid object experience is into some kind of flow, or a solid object moves through a fluid, then it experiences a force. If it is inside in a current, the force will be in the direction of the current, flow of current, and if it is moving inside a stationary liquid, the force will be against the motion. You can simply say the Stokes Law reiterates that there is a viscous force acting on the object flowing in, say moving in any kind of fluid, and that viscous force is equal to what we already know using the equation of viscosity. Force of viscosity is equal to minus eta times A dv by dy. So you might be thinking, why this minus, right? Minus means obviously this is against the motion, right? So this minus sign is showing that the direction of speed, direction of viscous force is against the relative motion between the two layers of liquid. Now, using the same equation, Stokes Law gives us an equation which we may call Stokes Equation, that gives force acting on a body which is falling through or which is moving inside a stationary liquid is equal to F equals to 6 pi eta R V. Now what are the parts in it? So you might have easily guessed that this force is the force which is acting on that object by the liquid against its motion. 6, you know, that's 6, number 6. Pi, you know that. Eta, you might again relate the two eta here, that is of viscosity, coefficient of viscosity. Now what is R? So we are assuming that this object is not any random shape but of a sphere. So this R is the radius of that sphere. And now V is the speed or velocity of that object inside that liquid. So using Stokes equation or Stokes law, we'll come to derive the terminal velocity. Let's go ahead and try that. So let's consider a situation. Somebody jumps from a plane. Sorry for my bad drawing here. Let us say this is a plane and someone jumps from here. What would you think? Initially the speed is definitely 0, vertical speed I'm talking about. But as the particle of the person who jumps, the speed grows, and that is obviously depends. The speed increase in speed is equal to g into t, means whatever. If someone has fallen for time t, the velocity v would be 0. Initially it was 0 plus gt. So you can say that speed will keep on increasing linearly, and obviously this will never stop. There will never be a constant speed, but this doesn't happen. What happens if someone jumps? There are two forces acting on that body or that person, or you might come to know that not only two, there are three. First, force of gravity, which is acting obviously down in the downward direction. Another is force of buoyancy. You might remember Archimedes' principle, and from that force of buoyancy. But where is that fluid air? That is the air. Air also exerts a buoyant force upward on any object whichever is present inside the air. So we all are experiencing the buoyant force. Another force, which is a variable force, is force of viscosity. And why this? Because that person who had jumped from the plane is moving through the air with some speed, and air has some kind of viscosity in it. And you can say this viscosity, or say coefficient of viscosity we are taking, is eta subscript air. Using these information, first the free body diagram of that fallen person or fallen object, and the viscous coefficient of viscosity of air, we'll find out the terminal velocity. And what is terminal velocity? First, terminal velocity is the maximum velocity that a fallen object attains. Means at some point the object gets a constant velocity. After that, its velocity doesn't change. So for that, for that velocity has to be constant. And for constant velocity, we know that acceleration would be 0, and for that mass times acceleration would be 0, or the net force is also 0. So we will equate the net force to be 0, and using that we'll find out the terminal velocity. So again we are equating the forces. So F net is equal to force of gravity minus force of buoyancy. What is buoyancy? The Archimedes principle, the buoyant force which is acting on the body which has just fallen off the plane in the upward direction because of the density of air, minus force of viscosity. And viscosity is again, force of viscosity is the viscous force acting because of the relative motion of that object in the air. We know force of, this is not F times G, you see that this is subscript G, so mass times gravitation, acceleration of gravity, mg, minus, what is buoyant force? Buoyant force is the mass of liquid or fluid that has been displayed. So what is the mass of liquid or the fluid? This is V, means obviously this is the velocity that, this is the volume of the object which is traveling through the air, times rho of air, density of air, times G. V rho G means this is, you can say, mass of the fluid which has been displaced into acceleration due to gravity, minus force of viscosity. Now what is force of viscosity? We have just discussed the force of viscosity is 6 pi, I think I wrote it somewhere, yeah, 6 pi eta RV. Now this eta here is of air, so I'm writing the subscript air. And now what is this R? So again I'm assuming this is not a person, I have just dropped a sphere from a plane, and this velocity V which will keep on changing. So obviously I'm assuming at the time when this has to be constant, so let's term as terminal velocity. From now on in our calculation we will use the term V term is equals to V to maintain our fluency of our calculation. So this will be the situation when the net force will be 0. The gravitational pull subtracted by the buoyancy, force of buoyancy subtracted by the force of viscosity. Now to solve it out, let us say what we need to find out, this V term. So we'll try to isolate this term here. We can say 6 pi eta air into R equals, into V I just said V term is V equals mg minus mass of air, or say volume of that object, into density of air times g. Let us isolate g here, m. So we can write m as density of that object into volume of that object minus volume of that object into density of air. Again, taking out v. This v is not velocity, this is capital V for volume times g into v object minus, sorry, this is rho object, density of the object minus density of air. Solving this further, what I need to do, I need to isolate this. So I'll take this whole side and divide both sides by that. Therefore, velocity, terminal velocity v equals volume g times volume v, sorry, capital V times g, small g, acceleration due to gravity, into rho of object minus rho of air. मतलब यहाँ हम डेंसिटी ऑब्जेक्ट की भी डेंसिटी कंसीडर कर रहे हैं और एयर की भी डेंसिटी कंसीडर कर रहे हैं, लेकिन जो वॉल्यूम कंसीडर कर रहे हैं वो हमारे ऑब्जेक्ट का था, वो स्फेरिकल ऑब्जेक्ट जिसका रेडियस हमने r लिया है. सो हम इसको रिप्लेस कर सकते हैं 4/3 pi r cube. You see, this is the volume for volume of a sphere with radius r. Now dividing this whole thing with this 6 pi eta air. What do we get when we simplify this? Let's see. Therefore, V equals G by everything. This comes out. We can cut out, cancel pi. We can cancel, I think there was one r here. I think we need to put an r. So I will also cancel one r with one r. So there will be r square here. That I'm getting. And this 6 is also getting cancelled with 4. So let me write the final result here. I'm taking a peek from my notes, and that gives me, yeah, 2/9 do I have anywhere where g is cancelling? No, g is not cancelling. So p object minus, sorry, again, this is not p, this is rho for density air to r square g by eta air. So terminal velocity equals 2 rho object minus rho air r square g divided by 9 eta air. Okay, so I think we are almost done for our this lesson. I'll try to wrap up from now. So what we have done so far is we have just discussed some concepts of fluid mechanics, one being viscosity, another Stokes Law, then terminal velocity, then streamline and turbulent flow. We just left with streamline and turbulent flow. If in a flow each stream is going in its own direction without intersecting with other, we call it streamlined flow or laminar flow. If something is happening, like you might have seen in the taps, that the flow is not very constant and after that it breaks into some drops of liquid, this kind of flow is called turbulent flow. And what is decided by what decides turbulent flow and laminar flow? This is given by Reynolds number. Reynolds number is a dimensionless quantity and it equals inertial force on that segment. Like if one segment of liquid is flowing and there's an inertial force, like the force that is pushing it forward, and one force is viscous force which is acting in between the layers, is called viscous force. This ratio is known as Reynolds number, and it is said that if this is smaller than smaller than 1000, the flow is streamline or laminar. Laminar is nothing but streamline, and if it is greater than 4000, it is definitely a turbulent flow. And in between 1000 to 4000, the flow may vary from laminar to turbulent and so on. It may sometime become laminar, it may sometime become turbulent. You will learn about this topic in higher classes, or say in some fluid mechanism, higher parts of fluid mechanism in engineering courses, etc. But for now, this much is all you need to know. Like even for JEE syllabus, this is enough. There might be questions where you need to have a better grasp of this concept, and we will cover some parts in later videos. And we will also cover Bernoulli's principle in later video, because we have a crunch of time today. So that's all for today. Keep learning. See you next time. Bye.